Okay, hi everyone. Welcome to ICS 295 on causal inference. Do you hear me? Okay, good. So today my plan is to continue to talk about counterfactuals. We started, Bruce gave us a very nice introduction on Monday, and I will continue. I will, let's see, okay. I will also do an overview, go a little bit in a fast pace on the first part, what Bruce covered, just to put us in the right mind. Actually, this topic is, I find it a little bit involved, and especially notation and stuff like that, it's require getting used to, so it will benefit us all to go over the basic concepts again, and then I will continue with non-deterministic counterfactuals. Any questions before I proceed? Okay. So first, we will overview the last class, and let's start with the notion, the three ladder of cause and effect that we discussed, or three rugs of cause and effect that we started with in the first few classes to have this distinction between the various queries that we normally ask. One is what if I see, then what if I act, and now what if I had acted differently. So we already went through the notion of seeing doesn't require the do operator doesn't, we can do that just by observational distributions if we have access to it. And what if I act, we wanted to really define cause and effect, and the do operator, which we covered, and we defined how to answer queries with a do operator. And now when we talk about counterfactuals, we are not, this is going up one step. And the point is that in order to answer queries at the higher level, you need something additional. So going from the second level to the third level, counterfactual, which we are now talking, we are now requiring new notation and some new definition of how to really address this issue. And here are, this is a slide that I had from a while back, and I will not go into these examples. We also saw some examples earlier. And so counterfactual subsumes the other levels, whether we call them higher or lower. And we will see that with the counterfactuals, notations, and definitions, it's possible to really express and answer all the other queries as well. Again, so we saw some examples that Bruce covered, the examples of driving in Sepulveda versus driving on the freeway. This is an example taken from Los Angeles, where I live as well. And this is a real life example. People always really, if they go to the valley from the city, and they have to debate whether to go on the freeway, which is filled with car, or on Sepulveda. It's hard to know, and you are stuck. Once you are in making the decision, you cannot, it's hard to change. So this was the guiding example. I remember this when I thought about this a few years ago. I gave this example. Had Hillary Clinton won the election, had Hillary Clinton won the election, had Comey not announced 10 days before the election, the FBI reopened the investigation. So this was just to show that every day, that's the questions that we are asking. The counterfactual queries are the ones that people are engaged in all the time. So the point is that we need a language between beyond the do operator. So So if we try to express the estimate of those solutions, we can come to an impasse, and we cannot write this counterfactual query using, sorry about that, using the do operators. It will amount to writing what is the expected time of driving if we go on the freeway by our driving time on Sepulveda was 1 hour. So there is the issue that we are referring here to two different worlds and referring to actual driving times versus hypothetical driving time. And that's not possible with using the do operator, which talks or refer to a single world. So the counterfactual notation is here. We simply use different subscripts to label the two outcomes that we are talking about. We denote the freeway driving time, y sub x equal 1 or y1, and it says that it denotes the Sepulveda driving time if it x, the subscript. Had we drove on Sepulveda, the driving time on Sepulveda is x equals 0, so it's y sub x equals 0, and in the freeway it's x equal 1. And we also have the actual variables x and y. So this would be the way we will express this query. And we can refer to two different worlds. Okay. So the definition of counterfactuals, and Bruce's slides were very polished, very nice. I'm just using some old slides that I have taken from the primer. They are more crude, but you have both, and it's just easier for me this way. So going back to this definition of counterfactuals, we assume that we have M, which is a structural causal model. It's defined by visible variables, exogenous variables, and a set of functions. And the exogenous variables, we know the potential domains of values. And U equal U implies a single entity of the population, for example, a person. And X as a function of U is a characteristics of the world. For example, salary of an individual, salary of Joe. So the counterfactual sense is Y would be Y had X been X in situation U is denoted this way. U sub X, Y sub X of U equal Y. And YX are any two variables that are visible, that are observed. Had X been X can be thought of as an instruction to make a minimal modification in the current model so as to establish the antecedent condition X equal X. So that's a philosopher engaged in these questions, how to really talk about counterfactuals, and the notion of minimal distance to the current world was a guiding principle. And in some sense, what we are doing here, the current definition follows that. Okay, so this was the example, I think, this was the example that was used for illustration. Suppose we have this structural causal model at the bottom, X equal AU and Y equal BX plus U. We can talk about, and we have for the exogenous variable, we have three values. And here we assume that the A and B equal 1 for in this illustration. We can, for every value of the exogenous variables, we can define all the variables that we are interested in. So it will be X and Y. And we saw that they, from this equation, they are getting this values. X is equal U, Y is equal X plus U, and we saw the values of the counterfactual variables Y sub 1, Y sub 2, Y sub 3, namely if X equal 1. This is assuming that the it's indexed by by variable X, and we can have the opposite symmetric or opposite counterfactual variable X with the subscript Y, had Y equal 1 or had Y equal 2 or Y equal 3. And we saw how we can obtain these values as a function of U. So the difference between, we talked a little bit about the difference between do operator and counterfactuals. The do operator is only defined on probability distribution, and we ask after deleting the equation associated with X. When we do X, we are talking about how to compute the probability or the expectation of Y given that we intervened on the world. That's the query. So it captured the behavior of a population under intervention. And in contrast, Y sub XU describe the behavior of a specific individual under such interventions. And in the last, what we are talking first is about deterministic counterfactuals, namely when the value, we get a value, a specific value for the query. So if M is the M sub X, this is small here, the M sub X will be, as we did before, the modified version of our model. Sorry about that. When we intervene on X, when we are the world we are interested in is where X equal X, the definition of the counterfactual a variable is given here. That's very important. So Y had X been X in the value of the U equal U is simply this defined by the right-hand side. Namely, we look at the mutilated model where M sub X, and we look at the value of Y in that for the same U. So the counterfactual Y sub XU in the model M is defined as the solution for Y in the surgically modified submodel M sub X. Or in words, we have here a description. Yeah, I already said that. So, so that is the basis for everything that we are going to continue to do. And there is one important consistency rule that is derived from that definition, that if we have in a current model two values, X equal X and Y equal Y, then if the counterfactual variable Y sub X, when X equal X, is simply Y, the value of Y that we have. And we can write it also in this form, but that's it's quite, when we have two values for X and Y, we can write it, we can combine this consistency into this equation here. Okay, so so we saw some examples, and this is an example where we had, where we had three variables. I think this is below we see the graph of this structural equational model. We have X, the time in remedial program, H is the amount of homework why students score in an exam, and the values here are taken as standard deviation from the mean. And these are the equations. And we assume that all the U factors are independent with this constant for the equations. So this would be our structural model. And let's assume that we observed an individual with these three values. And we ask, what would Joe's score have been had he doubled his study time? So I'm going again over an example that Bruce went over last time, just to refresh. So if we, maybe I will not go into all the details. The point is that we can first, this example will allow us to decide what is the world in which this is obeyed. And then we are looking at the mutilated model. And in that model, we can compute, we can force X. We can, the homework to be twice as much, let's say, and we can see what would be the value for Y. And that was, is following this general computational method for addressing counterfactual, which is the 3 steps for computing deterministic counterfactuals. And later on, we do that for the probabilistic counterfactual. So first is abduction. We have evidence, and we use this evidence to determine the value of U, the exogenous variables. And then we do some action, we modify the model by removing the structural equations for the variables in X. We want to answer the query on Y sub X and replace them with appropriate function, X equal X, to get M sub X. And then we do prediction, use the modified model and the value of the of U to compute the value of Y, the consequence of the counterfactual. So if we want to go through this, the meaning in step 1 explains the past in light of the evidence. Step 2 bends the course of history because we want to make changes minimally to comply with the hypothetical antecedent, X equal X. And step 3 predicts the future based on our new understanding of the past and our newly established condition, X equal X. So that's what we more or less, what was covered last time. Any questions before we proceed? Okay. Okay, so we will go through several things. We'll see how far we go. First, we will extend, we'll see that we can extend, we will talk about what does it mean, non-deterministic counterfactual, and extend the 3-step procedure to that case. So in non-deterministic counterfactuals, we can have uncertainty about the U variables. So counterfactual can also be probabilistic, pertaining to a class of units within the population. For instance, this is the example in the after-school program example. We might want to know what would have happened if all students for whom Y is the student score exam was less than 2 had doubled their homework time. So we want to refer not to individual unit, but a subsets of the unit characterized by using the exogenous variables. So in that case, we will have, we will extend it by having a probability distribution over the subpopulation, over the exogenous variable U. And it will induce a distribution on the endogenous variables V, PUV, And then we can compute not only the probability of any single counterfactuals like y sub x equal y, but also joint distribution of a variety of observed and counterfactual variables. So that's the general scheme. It's pretty much on a high level, quite straightforward. And it leads to non-deterministic three-step for computing counterfactuals, just extending the three steps we had before. So given evidence, E equal E, for a given individual, what would we expect the value of Y for that individual to be if X had been X? The expectation, we denote it. Now we will denote the query this way. So we want the expectation of Y sub X equal X condition on this evidence. And as usual, the evidence can conflict with the antecedent, and this is because we are talking, we are allowing in counterfactual to address different worlds. So this is the same requirement, the same addressing the same issues that we had throughout. And if we have this counterfactual query, the three-step process is defined this way. So abduction, we want, given the evidence, to update our probability distribution over U, namely to obtain the conditional distribution, PU, condition on the evidence. Second step, we want to modify the model by removing the structural equation for the variables in X and replacing them with the appropriate functions X equal X, yielding the modified model. And then prediction, we use this modified model and the updated probability distribution to compute the expectation of Y. Pretty straightforward. Okay, any questions? Okay, so let's just revisit the earlier example and add a probability distribution over the exogenous variables. So we had these two equations and we had this table, but now we also have a probability distribution over U that assign for U equal 1/2, U equal 2/3, and U equal 3/6. And we may want to compute the probability or the expected value of some queries. So let's do that. So let's compute the proportion of unit for which Y would be 3 had X been 2. So this is the query. We are interested in the counterfactual variable Y when X had been 2. And we want to know what is the probability of this event, that this counterfactual variable will take the value 3. So we do the simple things we do in probability when we have tables. We are looking at this variable Y sub 2, and it is 3 only in the first row. So it is 3 only for unit for the exogenous variables U equal 1. So the probability will be what? It's on the slide.
1/2.
1/2, yeah. And similarly to in other cases, for example, Y sub 2, this is the answer. So the other queries we can have, what is the probability that Y sub 1 equal 4? So we go here, we see 4 is only here in the third row, so it corresponds, it uncovered that the world that we have to look at is when U equal 3, and the probability of that is 1/6. Y sub 1 equal 3 is 3 here. probability will be third, and so on. Oh, here we have something that looks a little bit less simple. Probability of y sub 2 greater than 3. Greater than 3 corresponds to these two values. So for u equal 2 or 3, and that the sum will be half. Any questions? We can compute also much more complex stuff. That's obvious. We can compute the joint probability of any combination of counterfactual variables and regular variables, and then use the simple rules of probabilities, since, I mean, the definition of what the probability distribution means. For example, if we want to compute the probability that y2 is greater than 3 and y1 is less than 4. So this is a query about two counterfactual variables. Y had x been 2, and we look at the worlds where it's greater than 3. So we see that it's when u equal 2 and 3, it's satisfied this condition. But we also want y had x equal 1 to have a value that is less than 4, which will be u equal 1 and u equal 2. So we will have just 3, and just the second row satisfy both conditions, which will lead to this probability. And likewise, we can do for the other queries. How would we compute this? For example, the probability that y1 is less than 4, and that y, so here we have in the second query, we have a counterfactual variable, and we ask what is the probability that's supposed to be less than 4, and regular variables y and x, and we ask what is, they have to satisfy y minus x greater than 1. You have the answer here, but how would we compute it? So y1 less than 4 is satisfied by u equal 1 and 2. And y minus x greater than 1. So now we are looking at these two variables. Y minus x, this is not greater than 1. It's 2 minus 1 equal 1. So it's not, but these two satisfy that condition. So the conjunction is that the second row satisfy both, and the probability is 1/3.
So a quick question, is it possible to have more than one row of the U values be actualized when you're computing these counterfactual probabilities?
Yeah, here I think maybe this one is an example. What is the probability? What is the probability y sub 1 is less than y sub 2? It's, you see, all the rows satisfy that, and therefore the probability will be 1. Does that? Did you mean that?
Yeah, that's what I meant. That's what I meant. Yeah. So you when you have multiple rows, because U is considered independent, right? You just simply add up, right?
Yes, yes. This is like as if you have a probability, you have a probability table for every combination of the values of the variables, you have the probability of that event. So it's you are actually given the explicit probability distributions over all these variables in this simple example. So if you have an event that corresponds to 2 rows, it's the sum of the probabilities, as usual. Is that clear?
Yes, thank you.
Okay. Okay, so now again, we are now going to really emphasize again that do operators are limited and we cannot just use them. Obviously, they were limited in the deterministic case, so it will be an extension of the same argument. And also that we can, however, on the other hand, express do operator using the counterfactual variables. So here is the same example that we saw before. And this could be the structural equation model for the example. So just to really argue that the do operator is limited, suppose we want to compute the expectation of y had x been 1, a condition on z having the value 1, the skill level is 1. So this is the expected salary, y is the salary of individual with skill level z equal 1, had they received a college education. X equal 1 means receiving a college education, I think, for this example. So we want to answer, to really be able to express this query. Can we do it without these counterfactual variables? We would think that maybe this would work, namely the expectation of y condition on doing x, giving a college education, and the skill level, the post-intervention skill level will be 1. But this is not going to work because the do expression stands for the expected salary of individuals who all finished college and have since acquired skill level z equal 1. In this case, z is a post-intervention variable. And the salaries of this individual, as you can see in the graph, depends only on their skill and not affected by whether they obtain the skill through college or work experience. So in technical terms, we see here that conditioning on z cuts the effect of the intervention. Y will be independent of intervening on x, and obviously that's not what we think the answer should be, because in contrast, just reading how it is phrased, it is possible that some of those who currently have skill level z equal 1 might not have gone to college and would have attained higher skill, namely higher salary, had they gotten to college. So having this skill level could have been obtained in different ways. So in the do expression, we cannot capture this fact. So in general, the candidate, the actual expression that we want to capture, which is the expected value of y when x equal 1, condition on z equal 1, is not the same then as this do expression. And here is just another way of seeing that. So from the graph, you can see, based on what we know about the do operator, that if z equals 1, the expected value of y will not be affected by intervening on x. So if we are intervening on x and enforcing x equals 0 versus enforcing x equal 1, the expected value of y, if we condition on z, would be the same. However, the counterfactual query using counterfactual variables, as we suggested, this would be one query and this would be the other query, namely y had x been 1, condition on z equal 1, versus y had x been 0, condition on z equal 1, will not be the same. And that's another illustration that these two formats are not, forms of writing the queries are not the same. So this shows that the do operator is not sufficient to really express these queries that we are interested in. On the other hand, counterfactual notation can capture the do operator. Right? So this is in form of question. Can counterfactual notation capture the post-intervention single word expression? If we have this query here, can we express it using counterfactual variables? What do you think? I said already it's yes. And yes, because we are in a higher level in our ladder, and everything that can be expressed in the higher level can apply lower. And counterfactual variables are simply more flexible. How would we do it then? However, how would you express this query using counterfactual variables?
Did you do it by looking across all the worlds where the x value varies on y? Like if you're looking at y counterfactual on x, and y counterfactual on x equals 1, x equals 2, x equals 3.
So what would be, how would you write, yes, but how would you write the query? So what is the counterfactual variable you will define or use to express this question? So it's y sub x, right? Because we y sub x, and we would ask what is the expected value of y had x equal 1, condition on what? It's
on the world, yeah, on the world where z equals 1, right?
Yes, but we want to talk about the post-intervention. Z is post-intervention after x equal, we are intervening on x. That's the meaning of that query here. So this is how it can be expressed. So the translation would be to using counterfactual variables y sub x equal 1. We are interested in the world had x been 1. And we condition on it on when z value after intervention, which is just this counterfactual variable equals 1. So in general, is that clear?
Yes.
Okay. Okay. So in one way of really getting convinced that this is the right thing to do is realizing again that this is the definition. When we are saying the probability of y condition on intervening on x, do x, and z equals z, this is what we mean. We use Bayes' rule, and we can talk about the joint of y equal y, z equal z under the condition that we intervene on x. Namely, we see that the z is the post-intervention variable. Yeah, there is this a notion that if z, sometimes z is a pre-intervention variables when we condition on it, and there was some example where z was the age in that example, and it was not a post-intervention variable. I don't recall if we cover this conditional intervention, but in some cases where z is a pre-intervention, simply what is going on is that the z is equal to z of post-intervention. So it's the same variable, can be shown to be the same variable, And in this case, it is the same thing, namely the do, the query associated with the do operator and the query associated with the counterfactual variable will be actually the same thing. So there are these cases, but in general, we don't have equality. This is, in general, we have an inequality here. And if we want to translate the do operation and use just one set of notation, we can do that. Okay, so let's now look at another example, or actually the same example, but now let's assume that A and B are just arbitrary A and B. They are not just one. So the table depicts the counterfactuals associated. This is a different table. Before we just have the simpler example with y and x. Here we have three variables, y, z, and x. And we want to look at counterfactual associated with x. So we will replace the equation for x equal u1 with the appropriate constant 0, 1 and solve for y and z. So what you see here, we have two exogenous variables, u1 and u2, and they can have all these combination of values. And these are the three equations denoted here, three of the structural model. And it's easy to see, first of all, xu equal u1, so you see all the values. Z of u, z is equal, z is equal a x plus u2, so you can check and see that this would be the values. For example, if we are looking, if x is 0, z will be u2, which is 0, and it's very easy to see that these are the values that you will get for x, z, and y. And now you can just do and compute the counterfactual values as well, namely y sub 0 for each one of these u's as a function of using the modified equations, and you get these expressions here. I will not go into the details. You can do it yourself. So this is just what we will get, the table of all possible values. And now we can compute what we want. So let's say that we want to compute the expected value of y sub 1. This is this a column, condition on z equal 1. So condition on z equal 1, z equal 1 only here, which will give us actually the value a plus 1. B, there is only one value here. So these are simple examples that the expected value is actually determined by a single line, a single row. So we can get here, for this query, we can get a plus 1 times b, which corresponds to this value. And y0 condition on z equal 1. Y0 is this, namely it's y had x in 0. This is the different values. And z equal 1 is the case, the second row, and we will get b. We will get b, so we get b. And if we were to compute the other query, namely the expected value of y, intervening on x, this is the do, the second layer queries that we talked about. We have this and this. In one case, we intervene on x, setting it to 1. In the other case, we intervene on x, setting it to 0. We will get in both cases the value, the answer as B, and because, as we said, that once we set Z, the intervention doesn't have any impact, and we see here an illustration that it doesn't have any impact. On the other hand, in the counterfactual formulation of the query, we do see that there is definitely a different answer. Whether we are talking about the counterfactual query had X been 1 versus the counterfactual query had X been 0 condition on the skill level. So this is an illustration to this point that we saw before. So this is just, I think, just elaboration. It says, despite the fact that Z separates X from Y in the graph, in this graph, separate, we find that X has an effect on Y for those units falling under Z equal 1. So those who have skill level 1, had you given them different college education, their salary could have been different. So the difference between these two terms is AB, and it's not equal 0. Questions? So just continuing. So these examples were very simple because the expectation here corresponds, like in the previous cases, to just one row. But to make it, to emphasize that it's just a special case, let's assume that the constant A in our model is 1. If the constant A is 1, the Z will be 1 in both in row 2 and in row 3. So in that case, when we are taking expectation, we would have to take both of those into account. So the probabilities of these two rows, one is when U1 is 0 and U2 is 1. The other is when U1 is 1 and U2 is 0. They will have probabilities defined by the probability of U. And then we can then express the expectation that we are interested in using those probabilities. I will not go into that. You can just look into it and convince yourself that this is correct. But the point here is that we have, as expectation, we have to really weigh each one of these with the probability and sum them.
Professor, in that case, since both the rows still end up with A plus 1 times B, would it still have the same expectation regardless of
this is B, where Y1, where is Y1? It's A1 plus B and AB, no?
Oh, I see. Okay, I see.
A plus 1 time, yeah, right? So it's not the same.
Yes. Right. Sorry, I misread it. Thank you.
That's good. That's good. Yeah. Okay. So I think we are at the end of our times. I have a few slides about the graphical representation of the counterfactual. We will talk about it in our next class then. Any questions?
Yeah, I had a question, but it's just more, given I'm a philosopher, it's a little bit more philosophical of a question. I was kind of curious. We've been mainly using counterfactuals to address, or these counterfactual models to address counterfactual queries. Like, what would have happened had I taken the freeway instead of Sepulveda, which I did take.
I didn't get this. Can you start? I didn't hear the first few words.
Oh, sorry. Yeah, so far we've been using this framework to address counterfactual queries, right? Like, yes. What would have happened had the student doubled their homework, right? Given that they had an exam score of like 1.5 standard deviations above the population.
Yes.
Is there any other application for this stuff outside of just counterfactual queries? Like, are there queries, for instance, that are future looking, that this framework gives us answers for, that the ordinary do operation would not give us an answer for?
I think yes. I definitely am sure that many of the, I mean, in artificial intelligence, if you want, I mean, this is just a general answer, but if you are thinking about the goal of AI, which is to really create an intelligent, intelligent robot, let's say, he would have to communicate with other, so that maybe what you were referring at the beginning, namely not only for counterfactual queries, because that's my answer is, yes, we need to answer these queries, but you are asking whether there are maybe applications, real applications beyond just AI, general intelligence, right?
Right. More than just like asking like, well, about what would have happened, but also insert, like, I'm curious if this framework can give you
I think so. I think I cannot very easily answer that, but I think because I'm really not working in the applications in this area, but if you're thinking about just policy, I mean, people in economics, they are trying all the time to determine policy, or people in epidemiology, they are trying to see what would have happened had the policy would change. So is that not what you mean? You want be something else?
You're breaking up, or I'm breaking up, I guess. Sorry, I missed the last like 30 seconds.
There is a lot of noise, some ambulance going on in the background here. So I don't know if breaking up relates to that, but I barely heard you.
Yeah, I think that my internet connection was unstable. Sorry.
That's okay.
Yeah.
I don't know exactly what you mean. Because every example that I have in mind is a counterfactual query for something.
Right. Yeah. I guess I'm like here's a question. Like, does knowing something about what would have happened, for example, with an economic policy, does that lead you to be able to answer questions about future policies you may adopt that you wouldn't have been able to answer otherwise had you not had the answer with the counterfactual question?
I think so. Yes.
You think so? Okay.
Yeah, I definitely think so. I mean, why would the people? Well, let's leave it at that. But I definitely think that, and actually, this brings something else to my mind about your project. For example, I mean, you will have to do some project at the end. Everybody needs to really summarize the paper or talk about what they presented, but not necessarily. In your case, you presented material from the primer. You may be interested to search for a paper that talks about applications, or not necessarily applications, but current papers on counterfactuals. They may address this question.
Right. So yeah, I guess then before we leave, you did mention like a project at the end. So I was under the impression the project was the presentation, or part of the project was the presentation. Are you expecting also a written paper summarizing what we've done, or? Yes.
Okay. So in your case, I think you may want to really look at additional paper or additional work on counterfactuals. Otherwise, you will be just summarizing the primer, and it doesn't make sense to summarize it. I for example, thought the first thing that came to my mind is the original paper by Balki and Perl on that, but I don't it could be interesting from historical perspective to look into that. But I'm not sure to what extent it's different. I didn't read that paper, but in general, anything. And if you look at the work of Elias Birnbaum or other people from other areas, it could be interesting to really expand.
Okay, well, thank you.
Sure. Okay, so I'll see you all next time. Bye. Stop recording.